So, welcome back friends. So, um, in the last a few lectures we have looked at the momentum. In the last few lectures we have looked at momentum based solutions of the Dirac equation. Firstly, in the Dirac basis, the UV solutions of the Dirac basis, their properties, their what is the completeness relation, what is the uh, orthonormality relation, and so on. And then we started looking at special class of solutions of the Dirac equation, various limits. So, one of the limits was essentially, one of the conditions was that the massless limit of the Dirac fermion essentially, which gave you the Weil fermions. The other class of limits was essentially what so under the big class of Dirac fermions. So, we considered two particular classes. One was this class of m is equal to 0 and which we call them as Weil fermions. So, these are very important and the other one is the Majorana fermions. Psi is equal to, with the condition the particle is equivalent to antiparticle. So, these are extremely interesting objects essentially. So, these are different objects, so which are independent of each other, but they are all, because a Dirac fermion can be written in terms of either two Majorana fermions, at the same time also can be written in terms of two Weil fermions essentially. So, so under the big umbrella of Dirac fermions we have seen these two classes, okay. And now what, so far we studied only the free Dirac equation. So far we have studied only the free Dirac equation without any interactions. We briefly mentioned that if I put non-relativistic potentials, like putting a step potential and so on, so it will only lead to problems which are associated with Klein paradox or Zetter-Bitter-Gang and everything. So, the Dirac picture does not really work, meaning does not really solve, okay, the antiparticle situation essentially. With usual methods of quantum mechanics, like potential, okay, or wave function methods, leads to problems like Klein paradox. So, Klein paradox is essentially, this happens if you have step potentials, say for example, okay. So, this kind of classical potentials. So, classical let me call it as a classical potential. So, classical potential which is localized at a specific point. So, if I consider this kind of scenario in a relativistic regime, because Dirac-Lagrangian is nothing but Dirac equation with a classical like potential, like a step potential, or you can take anything delta function potential and so on. So, and you can try to solve it, and we will see one particular case essentially electromagnetic potential and so on. So, all this will lead to problems like Klein paradox, in the limit when the potential is very large compared to the mass of the electron, when the potential exceeds the mass of the twice the mass of the electron, essentially when the V is much larger than 2 me c square essentially. So, in this limit you end up having Klein paradox, the potential is smaller than this limit, you can still have sensible results. Klein paradox will lead to abnormal results like reflection coefficient is negative, transmission coefficient is greater than 1, and all kinds of nonsensical results essentially. On the other hand, we also have situation for considering wave function methods. So, this will lead to problems when you associate currents with them essentially. So, if you have currents associated with, now if you construct wave functions of the Dirac solutions, essentially if you take the U solutions and construct a solution with only U wave functions, but U or particle wave functions, and then smear it with some potential like we have seen it, and the moment you put in interactions, this will lead to rapidly varying currents, because the interaction can lead to production of antiparticle wave functions also, because the full wave the interaction picture always contains a connection between particle and antiparticle wave functions, and this will lead to problems like Gang, which is essentially rapidly varying currents leading to unphysical results, essentially leading to unphysical results. So, we cannot use the usual methods of quantum mechanics quantum mechanical approach will not work. Or usual methods, usual quantum mechanical methods approaches will not work. But there are some methods in quantum mechanics which are completely workable even in this particular case essentially. So, there are some, but there are some other methods which work. In the relativistic regime. So, this, what is this thing? What is this particular thing which is called what does it work in the relativistic regime? What is the one which works in the relativistic regime? The method which works in the relativistic regime is called let me call so okay. So, how to deal interactions quantum So, in the relativistic quantum framework, so what we will start doing are simple things. The full picture is a relativistic quantum mechanical picture in which everything is quantized, the field, everything, the Dirac field is quantized, okay. Everything, the full picture is the full picture is the quantum field theory essentially. The full picture is quantum field theory, which will be hopefully a next set of lectures, a different set of lectures. But what we will do in the what we will do here is we will do what we will do here is we will start with the basics of the what we will do here is we will use we will do is use Dirac like picture, but with interactions in propagator picture. So, we will still use Dirac, Klein Gordon and everything, but we will there will be always be a mediator for our case. Essentially there will always be a mediator for our particular scenario essentially. So, there is no action at a distance. So, you do not have localized potentials like here essentially space localized here essentially okay. You do not have localized potentials or things like that. So, you will always have a propagator like so there will be always a mediator in this interaction essentially that means there is always some mediator in the picture, but you will still use Dirac wave functions and wave functions of the photon and the photon or what I mean electron or something, and then try to see how to do these calculations. Essentially we will not do the full quantum field theory, essentially we will not do the full quantum field theory, is very complicated and it has to be done in a complete set of lectures essentially. But what we will start using is we will start using something called the propagator methods essentially. We will start using something called the propagator methods okay, which are a part of the quantum field theory. So, what we do is propagator methods with relativistic wave functions. And these give you the same answers as a quantum field theory. These give you the same answers as in quantum field theory and they set the picture for you okay, same answers in quantum field theory as in quantum field theory and except renormalization in full sense essentially almost same answers as in QFT at tree level. Okay, I should make the sense that they are essentially at tree level. At tree level they give you the same answers okay, as in for tree level process at tree level process. So, there is an advantage of doing this and they set up the algorithms for calculation, set up the algorithms for the calculation. So, you do not need to know the full quantum field theory, but you set up the algorithms of how to calculate various process. Various processes at tree level okay. At the tree level you can calculate this process essentially and gives you also the physics of renormalization and everything, but not how to calculate renormalization in real sense okay, okay. But gives the while it gives the physics it doesn't set up the accurate calculations. So this is useful for, so for example, this entire setup has been very useful. Now you may say that why this setup is useful and so on. So this setup is useful for certain cases. Say for example, you may have most most of the simple process you can calculate without worrying about the full quantum field theory. So that in that sense this course helps you for calculating. It sets up the propagator theory, it sets up the thing, you can calculate various things. Essentially from now on you can start calculating simple E plus E minus process or so on, so essentially Yukawa theory calculations and so on. So and we can also can give you the picture of renormalization, like what I said about the cloud, the electron positron cloud, why does it arise and everything, essentially where does it come from and so on. So and it also sets you the picture for so it gives you but it cannot completely calculate the calculations of renormalization. The full calculations requires a full quantum field theory because there are a certain limitations. So the accurate calculations of renormalization, effect of renormalization requires some more full quantum field theory. Okay, but for most of the practical problems, most of the practical simplest process, most of without going into higher order corrections and so on, so you can calculate. Okay, so you can calculate simple things without really worrying about. We will introduce the concept of Feynman diagrams, we will introduce everything essentially and then set up the thing. Another thing we hopefully we will try to do another thing we hopefully will try to do is do the relativistic corrections to the hydrogen atom. So all this is possible in this framework essentially. So these there are set of problems which can only be attacked by this particular framework, which is not full quantum field theory. For example, full quantum field theory cannot really do these calculations. Okay, so and now this set is also important for calculating not just for hydrogen atom, for calculating relativistic corrections of various kinds to non-relativistic systems. And there are several non-relativistic systems, not just hydrogen atom. There could be dark matter, which is non-relativistic. Okay, there could be models of dark matter essentially which have this kind of features essentially. At a more less abstract sense and more simpler sense is quarkonia. Quarkonia are essentially bound states of quarks. Okay, different bond states of quarks. Essentially, there are 2 body bond states, 3 body bond states, mesons, and so on. So these are different kinds of quarkonia, and the relativistic corrections and higher order corrections to the potential and so on. So can be calculated for this particular case, and this is very important because this is a non-relativistic system in which there are relativistic systems essentially, the relativistic calculations essentially. For all this kind of, this is a huge topic essentially, calculating non-relativistic relativistic corrections to the non-relativist systems under general categories. What we see is only a specific example for hydrogen atom, but This is a huge category of systems of which are very very important, which are generally undergo under the name of Korkoni, and there are several kinds of effects one can calculate essentially. So for all these features essentially we need these kind of techniques which we start dealing with essentially. So this is a precursor for quantum field theory, and so at the heart of this is what we already know in quantum mechanics is something called the scattering matrix. The scattering matrix is a transition matrix which takes an in state to an out state essentially. Okay. So if there is an in state, and it takes to an out state, this is called a scattering matrix. So the scattering matrix at the what is happening here essentially, there are two states which are almost interaction free. This is the crucial element of the entire process which we are discussing, the propagator theory or so on. So essentially how we do interactions, we always do with interactions in relativistic regime in this particular process. We start with the process which are asymptotically free essentially. So these are states which are asymptotically free, or the technical word is asymptotic. So they are far off, they are almost like free objects. So in other words, we start with wave functions. Which are solutions of free Dirac or Klein-Gordon or so on, whatever relativistic equation essentially, or Maxwell's equations. So those are your in states. These are identified in or final or out states. So that means these are the objects which we will see in your detector essentially in your experiment. So what we see, these objects which are, they are solutions of free Dirac equation. Free means independent of your interactions and independent of your anything, standard Dirac equation. These are the solutions, and these are the particles you see. Okay, is it a electron or a positron or a muon or a kaon, whatever essentially. They are your in and out states essentially. These are your in and out. The S matrix contains the interaction part of the in and out states. Now I am using the Dirac notation here for the in and out states. That is because I am using some sort of quantum field theory on my behalf essentially on the back of my head, and there is a specific process which happens in quantum field theory which tells you that this matrix element can be evaluated, and it gives you the correct answers and so on. So there is this specific process, but there is a specific theorem and so on. So but we will not worry about that, and we will leave that entire thing to a future course on quantum field theory 1 and everything. For the present we will just say that the S matrix theory works essentially, and it tells you that the interaction part is the one which mixes the interacts between, which acts at one specific space time point essentially at a specific space time point. So all the wave functions, the interaction is nothing but multiplication of all these wave functions sitting at one particular space time point. That is it, that is your interaction picture essentially. Okay, that is your interaction picture, and that is your interaction, that is your interaction. So what does it do? It the S matrix takes your in states to out states, taking into consideration all these interactions in the theory essentially. The S matrix contains the interaction picture of the in and out states at specific space time point and takes the in states, meaning incoming states, to the out states. Now everything we are going to consider it as a scattering essentially, every process we are going to consider it as a part of the scattering theory essentially. Everything will be considered as a scattering in relativistic features. Now there is a specific reason to do that, why we do that, and that goes back to the quantum field theory. Now as of now this all looks like words essentially, and this looks like words, but what is at the behind of this thing is that let us actually try to do an example essentially. Let us try to do an example, and then I will try to tell you what are what essentially, what are what. Let us consider an example. So the example we will consider is the same Dirac Lagrangian with EM electromagnetic interactions. So the Lagrangian is given by L, I will call it already QED, is equal to psi bar I del slash minus M psi. This is nothing but your free Dirac Lagrangian plus minus IE psi bar gamma mu psi A mu. This is how electromagnetic theory interacts. Now you remember that electromagnetic theory interacts like with the potential essentially, with the vector potential which is A mu. A mu is your vector potential. This we have seen in your when we wrote the interactions with the Klein-Gordon field. So this is how it looks like. This is your interaction picture, and then we write the kinetic terms for the A mu field, which is nothing but F mu nu, where F mu nu is nothing but del mu A nu minus del mu A mu. So now you see that there is only one interaction. This is a free Dirac equation part, interaction part, free photon part. So there are these three parts of the equation. The Lagrangian have been divided into this part essentially. This is the counterpart of scalar QED Lagrangian which we wrote down for the Klein-Gordon equation. This is a counterpart for the scalar QUD Lagrangian, which we wrote down for the uh, scalar QUD Lagrangian we wrote in the Klein-Gordon equation essentially. Now, this has solutions. What the S matrix is telling you is the first part of this thing has solutions which are free, which are your U and B and everything essentially, whatever particle antiparticle solution, and this is nothing but your interaction part, and this is for again the photon part. What it tells you is that, so this is a free part which is given like this, either it can be a U which comes incoming, or whether it is an antiparticle which can be is represented by an incoming particle, incoming antiparticle, which has opposite sign because this arrow represents charge, okay, the propagation of charge. So, this part, the free Dirac equation Lagrangian, has solutions which are particles and antiparticle wave functions, which are incoming particles and antiparticle. Now, the interaction part has an incoming particle or an antiparticle, okay, and this is a photon essentially. A mu is nothing but a photon field. Dirac field essentially is this, we will see a mu will become a photon field, okay. A mu is nothing but a photon field, and this has a vertex, this is called a vertex interaction part. So, this tells you that the interaction couples with a strength I e gamma mu. I e is this one and gamma mu is nothing but the gamma mu. So, this is called a vertex. So, this is called a vertex. This is called a vertex. And the third one, and you also have one more thing, is something called a propagator. We will see what is a propagator, which has a strength which is a solution of the free part with a delta function potential essentially, with a delta function potential of this free part, free photon part, this is called a propagator or nothing but a Green's function. Now, given this, what we have written unknowingly or knowingly, for each of these terms I have written assigned some rules essentially. For each of these I have assigned some rules for each of these terms, and these rules are nothing but Feynman rules. These rules are nothing but your Feynman rules. We will see in more detail how this happens essentially. These rules are nothing but your Feynman rules, and you can evaluate a typical process. Let us take electron coming in and seeing another electron and scattering it away. This process, okay, this process, okay, I can calculate, time is in this direction, I can calculate using, this is an S matrix elements where the in states are your electron wave functions electron wave functions, and this is your propagator, and this is an S matrix element, S matrix, where incoming state is an electron, outgoing state is also an electron, and you have the S matrix like this essentially. So you can calculate this S matrix elements, which is called amplitude, just by using Feynman rules essentially. Using the Feynman rules, wherever there is a wave function you put in the wave function, and wherever there is a vertex you put in the vertex, and this entire diagram is called a Feynman diagram. So we just use relativity and ordinary quantum mechanics, meaning a part of relativistic wave function solutions, relativistic wave function solutions, and what we are doing is calculating a relativistic process like E minus E minus going to E minus E minus. So we are thinking of already seeing, you already have seen that just from the Lagrangian I wrote some rules which are called the Feynman rules, and from these Feynman rules I can start calculating process which are like electron scattering process essentially, and this is pretty good, and so you do not need full quantum field theory to calculate any of these calculations essentially. Okay. But what I will do is I will justify each of these things essentially, how to get, we already justified the first part, this is solutions for the Dirac equation. I will justify how to write the vertex and what is the interaction picture, and then we will also see how do you get the propagator part, okay, how do you get the propagator part in the coming lectures. Okay. In the coming lectures we will see, we will formalize this entire thing, how to go about it, and then see its various implications, and how to do some elements of renormalization before we close the course essentially. Okay. I will stop here, and we will continue this discussion in the next lectures essentially. Okay. Thank you very much.